Before I begin my talk, I'd actually like to do a small survey. So how many of you in the room are developers, programmers? Almost everyone. How many of you would think or consider yourself also a designer? Oh, okay, quite a lot of you. And how many of you would consider yourself to be both developers and a designer? Oh, okay. So the main reason I'm asking is because in my talk is actually exactly the last group as in I'm trying to use a developer's perspective to approach design problems, but at the same time, you still kind of need the design mindset to fully understand your problem. So I'm going to go through to go deeper into two examples. I mentioned about the V&A museum project in my description, but unfortunately, I decided to go deeper into two projects rather than talking more. But if you're interested, you can come talk to me, or maybe maybe next year. So a little bit about myself. I did my undergrad at the University of Virginia, and I did engineering. So it's a very traditional school with a very good curriculum, but also a very rigid curriculum. And afterwards, I went to become a Java developer in Silicon Valley, but at one of the biggest software company at SAP. So you can kind of imagine why I was like, my life is meant to be more creative. And there's just no role model around me that can do kind of creative programming. So I decided to trade that off for a creative life. So I enrolled in a school in London called the AA School of Architecture. So it's a very specific school, and it's one of, I personally think it's a hidden gem, and I highly encourage anyone who wants, who is considering a change of career to, look into this school too, because some of the best architects, they do not come from a traditional background as an architect. They all come from different fields, and that's how, you make great things. And so they are one of the pioneers in proposing parametric design, and which is heavily using computational tools in architecture. So I was very lucky. I came in with a very good time. It took me a while to adapt to the design thinking as well. And afterwards, I actually went on to become a facade consultant in Europe, in Hong Kong. And then later on, I became an architect under one of my favorite architects in Tokyo. It's called a guy called Kengo Kuma. So today I'm going to share with you two projects I did because my background is still very different from the traditional architect. So pretty much I'm trying to use a developer's viewpoint, how we're trained with problem solving to apply to solve design problems. Everything I did here is very freestyle. There's no no school of thought or anything like that. It's pretty much like you have a problem. I'm just think of how I can use scripting to solve it. So you would ask, why? Why do we need scripting in architecture? So of course, there's many different use cases, but I would just generally say normally it's one of these reasons. So first with design, so the human mind is very limited in our imagination. But the main thing with parametric design is that if you identify certain parameters, for example, this is a beautiful project, by the way. It's done by some A students in designing a pavilion. And so if you want to identify, let's say the gap, is the width of the gap is a parameter, and this whole form, let's say it's generated by a script, then it can generate, if you vary the parameters, it can generate forms that it's beyond how you think. And of course, most of the times it's not a pleasant surprise, but you have very amazing forms that's generated through parametric design. And then, so let's say you have a beautiful form. How do you make about constructing it? You have to put it down into small pieces to construct it. And so that's a process what we call panelization, how we, you don't just go around and, let's say if you have a cake, how do you cut it in order you can optimize so that you have the same area for each piece and so on. So it's actually itself is a very interesting problem to solve. And of course, you need to extract all the data. So you're not talking about a few pieces, but you're talking about thousands and thousands of panels. You might have to measure all the angles and so on, up to very exact millimeters. So you need to have scripting to extract all the data. And budget. So Within the real world, money drives everything. So if the client say, oh, yeah, I love this design, but I just don't have the money to implement it. So you have to go back and be like, okay, I will change my design, try to meet a budget. So that's all the boils down to all these 4 reasons. So within architects nowadays don't design in 2D plans. So we now mostly work with 3D software. And the most common software we use is Rhinoscript. So Rhinoscript is a NURBS modeling software. I will go a bit into the basic concept of what NURBS modeling is. But and the scripting tool that I use is a library within the Rhinoscript software called Rhinoscript. It's basically written in Visual Basic. And everything runs within the software. So there's no dependencies. Once you open the editor, everything's set up for you. So now I'm a software developer, but now when you go into doing frameworks, you have this and all those dependencies that will take you ages. So you just dive deep straight into the logic, which is the best part of it. Everything is synchronous, so everything is very logical too. And so architects, nowadays, because a lot of architects are also trying to do this, but of course they don't have the programming training, and they're very visual people. So there is something like a kind of a visual programming where instead of functions, they have all these, what they call batteries are actually functions, and that's how you pass the data. You pass it through the wires. It's very interesting, and you get all the data through the wires. But I would not advocate anyone to do that because you can have situations like this where, and this is talking about a very simple script. Like, maybe talking about less than 100 lines of code, because you can't really iterate things within this visual programming, and if you want to do it, you still have to write script within the battery. So I always say to the architects, if you can drive a car, why would you ride a bike? So yeah, I just encourage anyone, or even architects, to learn programming. It's essential for how we think nowadays in this world. So NURBS modeling. So different software have different theory behind modeling. I wouldn't go too much into it in the math because I don't know. I just know that everything within Rhino is formed by surfaces. Surfaces are formed by isocurves, which, you see all these curves? Isocurves are formed by points. And all these points, so all these points are controlled, are what we call control points. So if you modify the control points, it will modify the surface. So if you the most fundamental concept is points, isocurves, surfaces. That's how everything is constructed in Rhino. And a little bit about the data types within this software, this 3D modeling library. So I would say the beauty of this is that it's actually very fun that what you program, you actually see. It's not like you program all this data and then you have, So if you input a point, you construct a service and you see a service and so on. So you see what I meant later. It's very fun. And so normally, how would you data-wise? How would you represent a point? So it's the XYZ axis. So it will be represented as an array of 3 double data types. And the second type is a line. So a line is represented as a string, but if you have a line input, you will be able to extract the start point and the end point, and you will be able to obtain the middle point, which is they will give you back an array of points. And then for a service is also represented as a string in the Rhino software. But then basically with a service string, you'll be able to obtain all the isocurves from that, and you are also able to, from the isocurves, you are able to obtain all the points from the service. So it's basically, you input a string, you get all these wonderful things that come back. It's still amazes me to this day. So a little bit about the common functions in the library. So for example, extrude curve. What would you think about extrude curve would give you? Well, if you have a curve, you extrude it, it gives you a surface. So that's how you construct surfaces. So you need to input a string, which is a curve. You have then extrude curve, and then it will give you a surface as which is another string as an output. And for example, the curve surface intersection. So what do you think? What will this class give you? A curve, and then there is a surface and it intersects, it will give you the intersection point. And then if it's overlapping on the surface, then it will give you the period of overlapping, which is the start point and the end point of the overlapping period. So this library will give you all this two-dimensional array of things that will, you can obtain the event type, which is point or overlap, and then from the different, array output of the array, it will give you, the intersection point and so on. So from then on, it's like you can go on to take the point to construct what you need to do further. It's pretty much like a visual puzzle. And split curve, how you want to split curve. So with curves, there's something with nervous modeling. So if you have a curve, A to B, of course there's like a lot of points along the curve that, because you're not talking about straight line, but it's talking about curve. And then in Rhino, the curve is 0 to 1. And if you want an exact point on that curve, what they call is a curve parameter. So it's like a fraction. So if you want 3 out of 64 is certain point and so on. So it's unique to each curve. And if you want to split a curve at a certain point, you need to input the curve and you need to input the parameter. And then it will give you an array of 2 splitted curves. But then let's say if you have a curve like this, you want to split at this point, then it will return you an array of 2 strings, which the first string is the first splitted half and the second half. And how would you know why or not it's this part being the first element in the array, and this is the second, and that relies on the curve direction. So it's very fun, right? You have to have this kind of basic understanding of geometry. But after you have this, you can, pretty much drive your car all the way down to generate very interesting architecture. So now I'm going to actually talk about how I'm using this library to solve to solve the potential problems in architecture. By the way, disclaimer, everything here is very freestyle. There was no school of thought that I followed or no mathematical model. I just saw a problem. I'm like, okay, why don't I just try to use this library to solve this? So this problem, this project was done about 5 or 6 years ago. Actually, I'm not young. So it was one of my first projects that I used Rhino scripting to solve. And it was done during my time as a facade consultant. So the role of a facade consultant is different, as in it's like you are an IT consultant, but you are not the person who's designing the system. So it's very much like that. The architect has all these design restrictions. They give it to me, and then I'll try to kind of help them solve a problem. So the biggest problem is they have this beautiful scheme where they have a podium, which is a shopping mall, and then they have this amazing tower. And all of them are what we call double curve services. And they have designed a very clever system to try to clad the entire system with flat panel glass, and they're all of the same size. And in between the glass, they have all these aluminum panels to kind of eat in the change in the geometry. But that comes to the next problem is budget. So all these panels are all different sizes. And one of the biggest costs of architecture is labor costs. The material aluminum panel is not too expensive, but in order to have each person catering to cut the different sizes, it's extremely expensive. So we are trying to limit the amount of types of aluminum panels. So I first encountered this problem by identifying that into different zones. So zone one is the green area. So zone one is more simpler because this is what we call a single curve service. So if you extract the iso curve along this direction, each curve has the same curvature. They're identical. But zone 2 is the corner areas, and that's the biggest problem. The biggest problem is because, so it's a double curve service, as in if you extract the iso curve at different points along the surface, it gives you a line with a different curvature. So, but for that pattern, if you have 8 modules on the top, you have to have 8 modules in the middle, but you have to fit that with a curve of a different curvature, different length. But we try to optimize the amount of panels. So that becomes a very interesting design problem. And then, so this is the system that the architect gave us. So don't ask me why it's 1,201.42. So it should be 1,200, but they gave us that number. But anyways, we're trying to, that's the glass size, and we're trying to use the same glass size across the entire surface. So with here, so you see all the triangular panes are aluminum panels. And those are the ones that are causing the problems, that have different sizes and so on. And so we have identified two types. So there's the yellow type is the one where we will align it according to the same alignment as the glass. And then the blue type is the one where we will kind of like, shift it in to kind of fit the global curvature. So we kind of identified that facade system. And then this is how it will propagate in 2D wise. So you know how when you start from one end to the other end, you go up, it will, in order to kind of fit that puzzle, it will go slightly slanted. And then, so in the bottom row, and by the time it goes up to the first row, the top row, it would have shifted by 9 modules. So it's just kind of identifying the relationship. And within that, you kind of have to fill in modules to fit in with the corner piece. So with this design problem, how we identified that the best way to tackle this is to kind of go back and revisit the design process to find a way to generate the panels from, to make a script to generate the panels from the ground up. We control certain parameters to construct all these panels. So you have a flat surface, you have all the floor slabs. How would you go about like putting that pattern into that surface? So I decided to try to use, of course, there's many, many ways to a problem you can use. Some people were suggesting to use vectors. You can, try to get a surface to do a grid system, that kind of stuff. So I was just like, I was just like, why don't we just do it simply? I would just use guide rails, because with the surface, you can extract the isocurves, and then if you extract the isocurves that relates to the relative, if you break down the component into certain key points, and it's like, as a kid when we were connecting the dots in a coloring book to form shapes, it's pretty much the same idea. You just extract all the essential different guidelines, they're all straight lines, and then it will refer to the level of the point of the module. And then you just simply, from then on, you just simply divide the curve according to your required length. And then you just connect the dots, and then you will form the panel. And the panel will be aligned according to the surface. So this is the script for the strategy. So first you produce all the guidelines, and all these guidelines is very simple. You can extract it from the Rhino library. You input the flow lines, which is given to you by the architect, and you input the reference service. And then from that on, the scripts, you can go through it to extract all the guidelines. It's a function within the Rhinoscript library. And then from then on, once you have all the guidelines, you can start introducing different module size. If I want to test like the entire module, we're talking about glass and the panel. Maybe I want to try a 500 mm width for the panel. Then I can, of course, along the entire length, there will be 15 modules. If I want to try 14 modules or 13 modules, I can vary that and see the effect. Because architects, they like to see how it looks differently. And then from you can produce all these points, and simply from the points, you can construct the glass surfaces. And all those glass surfaces will be aligned according to the surface, to the curved surface. And then, so we have solved the zone 1. But zone 2, how do you solve zone 2? It's, because on plan, everything is the same. So you can just use these strict guidelines. And then you can just simply divide it by the length, right? But in the curved corners, it's a headache. Because for the top isocurve that you obtain, it's a different curvature from the lower curve and so on along each row. And then they are not an arc. So you cannot simply use arc calculations to do it. It's basically a curve with the control points, like irregular control points, basically. So I have, for this one, it's basically a given that the length of the module next to the glass will be different along each row. But how do you know, what is the optimal length for this? And that's, here I have kind of identified that is an unknown. And we need to start with, we will have a variable that will kind of govern the first point that you would test it to. For example, if you have set a ratio of the glass is 1 and the panel ratio is 0.3, then you kind of know you'll fit 8 modules along the way. But you don't know the length of that panel. You don't know the exact length. You cannot make it as 300. It will be 320 something in order to be optimized. So that's actually a very simple, that boils down to a very fun and very straightforward design problem that can be solved by script. So that's something that, that actually took me a while to think about how to do it, because within the Rhino library, you can divide a curve by length. So you want to divide a curve by 3,000 mm. You can, and they will output you, points that on the curve that's 3,000 mm from the last point. But we are talking about straight glass. So we're not talking about distance. We're talking about displacement, what I call a line distance. And then how do you do it? You can just simply divide the curve. So my idea is that if you take the center point of one point of the curve and you construct a circle, and you get the intersection point between the circle and the line, and because the distance is the radius, it will be according to the length that you want. And so what I meant is, for example, like if you were, this arc length is not 3,000, not 1,200, but then the aligned distance would be 1,200, and that's where you will fit the glass. So that's the first iteration of the script. As in, you construct a circle, you obtain this intersection point, and that will become the center point for the next circle to obtain the next point for the aluminum panel and so on. So you just continue to iterate this. And of course, the length of the panel is a variable that you input in as your initial try. So you would, as a designer, you'd be like, okay, I think, I want it to be 8 modules, and it will be about the ratio will be about 0.3 to 1. It will fit 8 modules. And what will likely is, so you continue to use this method to obtain all the points, and it comes to the $1 million question, literally $1 million, because it's construction material. You have an edge condition. So the edge condition is like, it will be a gap, because this part, from then on, it will be the panels from zone 1. There will be a gap between the panels that you generate here to this zone 1 panel. And there is what we call tolerance, as in like, if the gap is less than 20 millimeters, you cannot see it. So you can just call it a day and move on. But you can't, right? Most of the times, it will come to like, 180 millimeters or something. And then that's what I call an edge condition. And with this one, it will, let's say we have 180 mm as the edge condition. And then the script will be like, okay, so now we need to shift the aluminum panel from 300 mm to 301 mm. So we'll do it by increment of mm. Well, what we'll do is if you have 8 modules, because it will first determine whether you can fit 8 modules. If you can't fit 8 modules, they will tell you to like, go back and change another number. But if you can fit 8 modules with an edge condition of 180 mm, so you would take the 180 mm, divide by 8, and then you will start again, like you see the different points, like I shift the points by 180 divided by 8 mm, and then go on. But the thing is, that's the thing, it would not exactly propagate the edge condition because this is a curve. Like the aligned distance is different. So you will keep iterating that until it meets the tolerance level, which is, let's say, 10 mm. But the world is not ideal. There are cases where let's say if your panel is 324 mm, so you increase by 1, so 325, right? So maybe before the edge condition is, let's say, like 22 mm. And then you're like, no, you need to go back and re-optimize it. But if you increase it by 1 mm, then maybe it will be negative, as in it will eat into the next zone 1 panel. So there might be situations where it does not, you cannot obtain a configuration that would meet the perfect edge condition. And that's when we will brutally, that's up to 200 runs. If it couldn't find a solution, I would brutally set it to use the arc calculation, just, okay. So, you cannot accept that all the same, we have the same length. Just, maybe we'll assign some panels according to a different length and call it a day. Yeah. So this is pretty much the layout of how the iteration of obtaining these points is. And this is an important class within the script. And then after you've set up the points, and then generating the next layer of points is much more straightforward. You can just, what we use a function called curve closest point. So it will, so you have a curve here, and you have a point here, and you have a relative curve down here. You can just use curve closest point to obtain the relative point on this other curve. And then again, it's, after you've obtained all the points, you just join the dots and form the panels. And then for this lower level, then you do the same iteration again to find the perfect configuration. But of course, because the top layer, you have set it up to be 8 modules. So the lower level, we will do it according to 8 modules as well. And yeah, so this is pretty much the summary of how the script will run. So you have the top, the script input is you have the reference service, you define the top ratio of the panel to the glass, and that will govern how many panels there are. And it will keep doing this to find the optimal panel arrangement for the top and for the next layer, and so on, from top down. So you can see why everything is synchronous. And yeah, and everything is very logical, as in architects do not, for us as developers, we will have the power to be able to help them break down a problem like that. But architects, they would just, and then afterwards, of course, we need to output the data. So within the script, Visual Basic, I think that's one of the reasons why the developers chose to write this library in Visual Basic, because you can simply call the Visual Basic functions, which they can call Excel directly, and output all the data in Excel. Unfortunately, because of the time of this talk, I don't have time to go through all the exact code and how it's run within the software. But within the next example, I'm going to show you how it runs in Rhino. So this is a different project that I did, actually this time as an architect. So with the good thing with being an architect is because before we were given a lot of restrictions to design how the module is designed is given by the architect. By the way, the architect of the previous project is very smart. I think that system is one of the best, what we call component-based design system I've ever seen. And it gives you a ground to have all these fun mathematical things to play with. That's what I would think that's a good system. So with this one, I worked directly with the architect who designed this game. This is a museum in China. Unfortunately, the project was kind of on hold, but maybe one day you'll see it. And so we initially, Kengo Kuma, once he got this project, and he was like, oh, I wanted to make us a museum gallery with a spiraling surface. That's the only condition he gave, and also cost. So he wants to panelize it with straight panels, straight, like what we call flat glass panels, not doubly curved panels. But this is a spiral surface is a double curved surface. So here I first identify how you do this spiral surface. So you basically have a upper spiral, you have a lower spiral, you have an inner spiral to form the, and then you see these are the slabs, so the gallery space in between. This is more like an architectural thing, but here we are trying to optimize and find out the relationship, how you can achieve the required surface area with a spiraling surface. So the angle of the inner and spiral curve could affect what we call GFA, the area of the geometry, but this is not there's no coding involved in this. But okay, so I have this this surface identified. Then I start to go and think about, okay, so how would you panelize that surface? Flat glass panels, that's the only condition. And so of course, you can go in just to what's the best way to try to cut it first? So that's I start doodling in my notebook. And then I have identified 2 ways to cut the surface or to divide the surface. One way is you can, along the spiral, you can divide what's the width, the aligned width of the glass, and then you just divide using the same way that I mentioned in the last exercise, where you construct a circle or a sphere to obtain the intersection point to get the aligned distance. And the second way is to you have a cutting plane. And then you just take the center point, you rotate it to rotate by same angle to obtain the divisions. But the thing is, I decided the first way is better because the center of rotation method to obtain the division, it's actually not much you can control because it's such a big scale. And the angle that you can rotate is, well, if you rotate a little bit, you're already making divisions that's beyond the fabrication limit. So that's why you chose the first method. So with the first method, you are able to obtain all those points. And again, it's all about connecting the dots in this exercise. So now we can go into the individual panel and see how we will construct the panel. So we want them to be glass surface, right? So if you look at this problem, so if you were to just simply obtain the points, it will be a doubly curved glass surface. So in order to make it flat, you have to take point 1 and point 3, take that line and copy it to point 2. But if you do that, then it will create this kind of what we call a offset from the upper spiral. But that's the beauty of why, as an architect, so as an architect, you are able to design the system. And then that kind of drives me to, okay, then in that case, if you have an offset point, why don't I just put a wooden glass fin to conceal it? And then in the end, in any effect, if you were to copy that, it would become like a turbine shape or like a fan shape thing. And it kind of became that design narrative. So when, for example, when Kengo Kuma-san, he goes on to be like, oh, this gallery is, trying to represent the Chinese culture with the Chinese fan. But, it's basically just to, solve a design problem. But that's, yeah. And so this forms the basic system of the facade. And from then on, I can start to construct a script to generate this. So I go into, of course, this is just very plain if you just to copy it and have this turbine across. So you try to introduce small, interesting design features. So I also went back to the notebook and start to find out what are the parameters I can vary to make it more interesting. And then, if you recall, here I have chosen the method of method 1. I can so in this case, the variable I can input is actually the width, top width and the bottom width. So I can use that to control how my geometry would work. So here I was just thinking ooh, it would be quite cool if you're walking along the spiral and the distances between, you go from a wider glass to a tighter glass and back to a wider glass again. So how you see you go from a tighter width to a maximum width and back to minimum width and so on as a design parameter. It will be quite fun. So okay, this time I'm going deeper into the code. It's a relatively simpler code. So within the Visual Basic, you have to design the user inputs. Well, you can't generate something from nothing. So you still need to input something. And so you need to define what, I've identified a variable called intensity. Intensity is basically controls how drastic this change would be. And then there's the, I call it T detector. Basically, it detects which zone, you're in increasing zone or decreasing zone and so on. And you have to define what's the smallest width, the biggest width, and then you have to input all the spirals to generate all the points. Yeah, and then you define the center point of this cutting sphere to obtain the intersection point. And then you also have to define what's the width of so let's say it's the first panel within the increasing section. What would the width be? And then the next panel and so on. So the width is governed by the intensity. And then you also save the data for outputting to Excel. And then you would construct the first sphere. Okay, we use the sphere, not a circle, because the curve is not a plane, but it's spiraling up. So you need a sphere in order to obtain the intersection point. And then you obtain, let's say you start with the lower spiral, you obtain the next point, and then you need to obtain the relative point on the upper spiral, and then you construct a bigger sphere to obtain that intersection point. And then you construct glass surface, and you make the panels and fins, and then you output the data. So okay, enough talking. Let's see how the script will run in action. And then, so first, when you want to run the scripts, so you need to call the edit script, and at the script editor. And then you start running the script. So you need to input all the variables that we have defined. So I set the intensity to be 50. And then you have to, that's when you enter like all the minimum glass width, the maximum, so you can kind of control it in terms of fabrication-wise. And then you also control like how that slanted length would be. It's 15 meters, so yeah, it's a crazy big piece of glass. Maybe that's why they put the project on hold. I don't know. Yeah. So and then the script will start constructing all these like spheres to obtain all the intersection points. It's really fun, right? Because what you program, you can actually see in action. So yeah, and it's actually very soothing after you programmed, and then you just watch the ball, and then yeah, and then we'll start constructing the glass panels. And of course, like here, because the viewport needs to reconstruct the geometry, so it's slower. But if you minimize this, it doesn't need to reconstruct it in front of you. Then this process is you're talking about like seconds, no, milliseconds. So you get this within 1 second, yeah. But yeah. But there's nothing better than seeing your code, come in action. So yeah, and. Yeah, so you see all those like offset points is like being concealed by the aluminum fin, the decorative fin, and as you reach the end of the spiraling surface, then it will actually output all the data. It will call Excel directly and output all your data, according to like yeah, basically all the data that's one within the script. Yeah, so this is it. And this is like kind of the final result that you will get, gradual like zones that you will go to an increasing zone, decreasing zone, increasing zone, and so on. And since the intensity is a variable that you can change within the script, so you can, of course, the effect is not that different, but like you can test different intensity as to how it will look in general in the form, and you can also analyze the data to see which configuration has the best, will allow you to produce the best cost. Yeah. And then, of course, like we're talking about 15-meter long glass. Like, the biggest glass that's ever in this world is 18 meters. And that's the Apple Store in I think it was the Apple Store in Hong Kong. And of course, our client is not Apple, so they don't have that budget. So yeah. So we'll have to like further think about like breaking the panel down, and what comes as a obstruction to the design. Actually, it's something that turns out to be something that you can play with. I go back to my notebook and then start like thinking about what are the best placement of what we call this breakpoint for the glass. This is something we call transom. So what's the best way of how we put the transom? And then, because we have a script as a basis, we can just, I can just write a new class to construct all these different like places where you can put the transom, and you can produce all these things can be generated, just by putting a different variable, and within the script it runs within seconds. But imagine like modeling this for an architect, because every piece of glass you have to measure it and model it according to the exact dimension. This will take an architect talking about like weeks, days, if not months, to generate different effects. So this will actually really affect, and even for them, a lot of them, the human mind, we cannot imagine things to be a certain way. You will only know when you generate the script. So this is actually a very new and interesting design tool that is in the hands of the power of the developer. So we are very powerful, not just within the development world. And here, this is a little bit more on the architectural design part. But for example, like before, when we copy the point, we would copy it to the point of the lower spiral. But we can copy it according to the top line, and then it will produce a different atmosphere within the building. Yeah. But so we can identify the different cases again, and that would just you tweak a little bit in the script, and then you will be able to generate the different effects of it. This is, again, to showcase the different effects of it. By the way, my presentation is very visual because before I was presenting to architects. So that's why you kind of have to diagram everything to kind of show visually how it works. And so this is a very powerful library, but there is also a lot of limitations to it, because technically they designed this library for hobbyists. So there's nothing. They have no idea of like states and so on within the program. So by states as in like, so let's say if I were to run the script and I have run until I have generated all the points and I have a bug in the code or there's unclean geometry. And then, but let's say after it outputs all the points, it will have like 133 points and 132 points generated. And so from then on, let's say your script breaks from there. And then you have to go in, you have to check why it breaks, and you have to run the script from scratch again. Within the black box of Rhino, it lost all the data once you terminate the script. This is a relatively simple project, but if you're talking about like, if you have to make like 28 of these services, so that means like, you lost all your data and you have to rerun it from the beginning. So it would be great if they can actually have something that, you terminate it here, you can save the state, and then you can start the script from that on. And also there's no testing framework. So how do you test it? So what you test is you just pretty much run the script, it breaks, you check the data as to why it breaks, and you run it again. Or if it doesn't look right in the model, it doesn't, So no testing framework, no snapshot testing, yeah. So that's what causes a lot of late nights. And okay, so I'm not an architect now. How I see it can be applied to a lot of like application outside of architecture. So this is something that I've actually always envisioned since as a master's student. So this way, how architecture is not, it cannot affect you just visually, but it can really affect you your daily operations in a building. So my master's thesis is to propose a solution to solve the congested underground stations. What if the main problem of causing congestion is pretty much your ticket gates? What if we can eliminate the ticket gates? We can, because we have augmented reality. And if we combine it with sensors, then we can kind of detect whether people has paid or not, once they pass the pay zone and so on. So this is one of the reasons why I'm going back to the development world, and this is one thing that we can use this kind of mindset of doing 3D programming into software development. Yeah, this is just some dream scenarios that I did before that we can propose as an architect. And so yeah, this is it. So I'm now a software developer, so, but I have a few other projects that I did before. If you're interested, you can like ping me on Twitter. I'm not very often on Twitter, but now I'm back in the development world, I have to be back on Twitter. So that's it. Thank you.